Welcome to this coding solution. Today, we'll be exploring problem number 345, titled Reverse Vowels of a String. In this problem, we'll focus on reversing the vowels in a given string while keeping all other characters in their original positions. Stick around as we dive into the intuition, approaches, and techniques to solve this challenge. In this problem, we need to reverse the vowels in a given string while keeping all other characters in their original positions. A vowel is defined as one of the letters at E, I, O, U, or their uppercase counterparts. For example, the vowels in the word apple would be A and E, and both need to be reversed while preserving the order of the other characters. The input to this problem is a string S, which consists of printable ASCII characters. The output is also a string, where only the positions of the vowels have been reversed. It's important to note that consonants and other symbols or spaces remain untouched in their original positions. This ensures that the transformation affects only the vowels and nothing else. Let's look at an example to clarify the problem. Suppose the input string is S equals hello. Here, the vowels in the string are E and O. To solve the problem, we reverse the positions of these vowels while leaving all other characters, such as the H, L, and the second L, in their original places. As a result, the reversed string becomes holly. This example demonstrates the core idea: vowels are swapped, and everything else remains unaffected. Now, consider another example where the input string is S equals LeetCode. The vowels in this string are E, E, O, and E. If we reverse their positions, we get O, E, and E. The original order of the consonants and non-vowel characters, such as L, T, C, and D, remains unchanged. Therefore, the output string becomes LeetCode. This example illustrates how the algorithm handles strings with multiple vowels, ensuring that all vowels are reversed correctly. Here's a third example to highlight another aspect of the problem. If the input string is S equals AA, the vowels are at enda. Reversing their positions results in the string AA. Notice that the case of each vowel is preserved in the output. This means the algorithm is case-sensitive and treats uppercase and lowercase vowels as equivalent for the purpose of reversing, but it maintains their original case after swapping. Finally, let's address some important edge cases. First, if the string contains no vowels, such as B, C, D, F, G, the output should simply be the same as the input because there are no vowels to reverse. Second, if there is only one vowel in the string, like an ABC, that vowel remains in its original position since there's nothing to swap it with. Third, if the string consists entirely of vowels, such as AIOU, the result is the reverse of the entire string, which would be UIA. Additionally, the algorithm must handle mixed-case vowels correctly, ensuring that uppercase and lowercase vowels are swapped while preserving their case. Lastly, because the input string can be very large, up to 300,000 characters, the solution must be efficient, with an optimized approach to handle these constraints effectively. To begin, let's consider the brute force approach to this problem. The intuition here is fairly simple. We identify all the vowels in the string, collect them into a separate list, reverse that list, and then put the reversed vowels back into their original positions. This method involves multiple steps. First, we traverse the string to locate all the vowels. Once we have them, we reverse the order of these vowels. Finally, we perform another traversal of the string, replacing the vowels with their reversed counterparts. While this approach is straightforward and easy to implement, it has significant drawbacks. Specifically, it requires multiple passes over the string, which increases the time complexity to O(n²) in the worst case. Additionally, we use extra space to store the list of vowels, resulting in unnecessary overhead. These inefficiencies make it less suitable for handling large strings. Now, let's explore the optimized two-pointer approach, which addresses the inefficiencies of the brute force method. The core idea here is to reverse the vowels in the string in place, without using additional data structures. This is achieved by using two pointers, one starting at the beginning of the string and the other at the end. The key observations that make this approach effective include using a set of vowels for O1, lookup time, and skipping non-vowel characters to minimize unnecessary comparisons. With this setup, the two pointers move inward, stopping when they encounter vowels. At this point, the vowels are swapped directly in the string, and both pointers continue inward until they meet or cross. This method avoids the overhead of collecting and reversing vowels separately, making it significantly more efficient. The two-pointer approach offers clear advantages in terms of complexity. In terms of time, the method operates in O(n), where n is the length of the string, since each character is processed at most once. For space complexity, it is O(1), because no additional storage is required beyond the input string itself. These characteristics make the approach fast and memory efficient, especially for large inputs. Additionally, there are alternative approaches worth mentioning. One example is using a stack to reverse the vowels. Here, vowels are pushed onto the stack during traversal and then popped in reverse order during a second traversal to replace the original vowels. However, this requires the extra space, where v is the number of vowels, making it less efficient than the two-pointer approach. Another alternative involves using regular expressions to match and replace vowels, but regex operations introduce overhead and don't provide substantial benefits compared to simpler methods. Given these considerations, the two-pointer approach stands out as the most efficient strategy for solving this problem. It achieves optimal time complexity of O(n) and space complexity of O(1), ensuring it can handle even very large strings with ease. Unlike the brute force method or the stack-based approach, it avoids additional data structures and performs all operations in a single traversal. This makes it not only fast but also resource efficient. By directly swapping vowels in place, it eliminates unnecessary overhead and simplifies the implementation. In summary, the two-pointer approach is the clear winner, offering a balance of simplicity, efficiency, and scalability, making it the ideal choice for reversing vowels in a string. To solve the problem of reversing vowels in a string, we start by breaking down the task into smaller components. First, we need to identify all the vowels in the string, which include a e, I, o, u, and their uppercase counterparts. Our goal is to reverse the order of these vowels while keeping all other characters in their original positions. This means that non-vowel characters remain untouched. To implement this, we initialize a few data structures. We use a list to temporarily store the vowels as we traverse the string, and we convert the string into a list of characters for in-place modifications. This is necessary because strings are immutable in languages like Python. The next step involves looping through the string to identify vowels. Using a helper function or a predefined set containing all vowels, we can determine if a character is a vowel and then append it to a separate list in the order it appears. This prepares us for the next phase, which is to reverse the list of collected vowels for reinsertion back into the original string. Once we have collected all the vowels, the next step is to reverse the list of vowels. This ensures that the last vowel encountered in the string becomes the first vowel when we reinsert them. After reversing this list, we proceed to reinsert these vowels into their original positions. To do this effectively, we iterate through the list of characters, and whenever we encounter a vowel, we replace it with the next vowel from our reversed list. A pointer is used to track our position in the reversed vowels list, allowing us to sequentially reinsert the vowels in their new order. Finally, after all the vowels have been replaced, we reconstruct the string. Since the character list has been modified in place, we can join it back into a string and return it. This completes the process. A few key insights make this algorithm efficient. First, by traversing the string twice, once to collect vowels and once to replace them, we achieve a linear time complexity. Using a single list to store vowels minimizes memory usage, and modifying the character list in place avoids unnecessary copies of the string. Additionally, reversing the vowel list ensures that the original order of non-vowel characters remains unaffected. Handling edge cases is an important aspect of this algorithm. For instance, if the input string is empty, we simply return an empty string. If the string contains no vowels, the original string is returned unchanged since there are no vowels to reverse. For strings composed entirely of vowels, the reversal process just reverses the entire input string. Another consideration is mixed case handling. Both uppercase and lowercase vowels are recognized and treated equally, ensuring that the algorithm works for strings with varying cases. Regarding data structures, the use of lists is central to this solution. We modify the string using a character list because strings are immutable in many programming languages, and a list allows for efficient in-place edits. To identify vowels, we use a set, which provides O(1) lookups, making the vowel checking process efficient. A separate list is used to temporarily store vowels as they are collected, ensuring that we can reverse them directly without additional operations. In terms of complexity, the time complexity is O, n, where n is the length of the string. This is because we perform two traversals, one to collect vowels and another to replace them. The space complexity is O, v, where v is the number of vowels, as we store them in a separate list. Here, we dive into the code implementation. The function reverse_vowels begins by defining a set of vowels for quick lookup, containing both lowercase and uppercase vowels. The string is converted into a list of characters to enable in-place modification, and an empty list called vowels_list is created to store the vowels as we traverse the string. The first step is to collect vowels. Using a loop, we iterate through the character list and check if each character is a vowel by looking it up in the set. If it is, we append it to vowels_list. Once all vowels are collected, the list is reversed. This reversal ensures that the vowels are ready to be reinserted in the opposite order. Next, we replace the original vowels in the string with the reversed vowels. Using another loop, we iterate through the character list, and whenever we encounter a vowel, we replace it with the next vowel in the reversed vowels_list. A pointer, vowel_index, keeps track of our position in the reversed list, ensuring the replacement occurs sequentially. Finally, the modified character list is joined back into a string, which is then returned as the result. For example, when the input is hello, the output will be holly, as the vowels E and O are reversed. To further illustrate the algorithm, let's look at another example using the string LeetCode. First, we collect all the vowels in the string. As we traverse LeetCode, we identify the vowels E, O, and E, which are collected into a list. Next, we reverse this list, resulting in E, O, E, E. The next step is to reinsert these reversed vowels back into their original positions. Starting with the first vowel position, we replace the original vowel with the first vowel from the reversed list, then move to the next vowel position and repeat the process. For the string LeetCode, this results in the modified string LeetSeed. This example demonstrates how the algorithm handles strings with multiple vowels, ensuring that the reversal is accurate and the positions of non-vowel characters remain unchanged. The output for this input is LeetSeed. The final step in the example walkthrough is to complete the reinsertion process for the remaining vowels. Starting from the beginning of the string, each vowel is replaced with the corresponding vowel from the reversed list, one by one. For LeetCode, the vowels E, O, and E are replaced in sequence, resulting in the final string LeetSeed. This demonstrates how the algorithm ensures that vowel order is reversed while maintaining the original positions of all non-vowel characters. By following the outlined steps, the algorithm efficiently handles the task, providing the correct output for any valid input string. This concludes the walkthrough of the example, highlighting the clarity and effectiveness of the approach in reversing vowels in a string. This Python solution solves the problem of reversing vowels in a string while maintaining the positions of non-vowel characters. The approach uses a two-pointer technique for efficient processing. First, we define a set of vowels, AIOU and AIOU, to identify which characters in the string are vowels. This set allows for O(1) average time checks for membership. Next, the input string is converted to a list because strings are immutable in Python, and we need to modify the string in place to swap the vowels. Two pointers, left and right, are initialized to the start and end of the list, respectively. These pointers will move toward each other as we process the string. The main logic resides in a while loop that runs until the left pointer meets or crosses the right pointer. Inside the loop, we first move left forward until it points to a vowel or crosses the right pointer. Similarly, we move right backward until it points to a vowel or crosses left. Once both pointers point to vowels, we swap the characters at these positions. After swapping, both pointers are moved inward, left is increment, and right is decrement. This process ensures that vowels are reversed step by step while all non-vowel characters remain untouched in their original positions. Finally, after the loop completes, the modified list is converted back to a string using join, and returned as the result. This solution efficiently handles the problem with a time complexity of O(n), where n is the length of the string, since each character is processed at most once. The space complexity is O(n), due to the conversion of the string to a list. This implementation also handles edge cases such as strings with no vowels, strings with only vowels, and empty strings. Here, we start by importing the necessary utilities for our implementation, and then define the solution class with the reverse vowels method. The first step inside the method is to create a set of vowels, which includes both uppercase and lowercase characters. This set will help us quickly check if a character is a vowel. Next, we convert the input string into a character array so that we can easily modify it in place. To reverse the vowels, we use two pointers, left, starting from the beginning of the array, and right, starting from the end. The goal is to move these pointers toward each other, swapping vowels when they are found. To achieve this, we first move the left pointer forward until it points to a vowel. Similarly, we move the right pointer backward until it also points to a vowel. This ensures that only vowels are targeted for swapping. Once both pointers are positioned at vowels, we swap the characters at the left and right indices. This is done by temporarily storing the value at left in a variable called temp, assigning the value from right to left, and then placing the stored temp value at right. After the swap, we increment the left pointer and decrement the right pointer, bringing them closer together for the next iteration. This process continues until the pointers meet or cross, ensuring all vowels are reversed in the string. Finally, we convert the modified character array back into a string and return it as the result. This approach is efficient, as it processes the string in linear time, making it suitable for large inputs. To solve this problem, we start by initializing a set of vowels, both uppercase and lowercase, so we can identify them easily. Next, we convert the input string into a list, which allows us to modify individual characters since strings in Python are immutable. For the example input hello, this gives us the list HELLO. We also initialize two pointers, left at the beginning of the list and right at the end. The goal is to move these pointers inward while swapping vowels they encounter. In the first iteration, the character at the left pointer is H, which is not a vowel, so we move left to the next position. The character at right is O, which is a vowel. Since we now have a vowel at right and a vowel at the new left position, we swap them. After the swap, the list becomes HOLLE. Finally, we move both pointers inward, left increments to 2, and right decrements to 3. In the second iteration, the character at the left pointer is L, which is not a vowel, so we increment left to the next position. Similarly, the character at the right pointer is another L, which is also not a vowel, so we decrement right. At this point, left and right meet in the middle, which means we've processed all the relevant vowels. The loop terminates, and we convert the modified list back into a string. Joining the characters gives us the final result, Holly, which we return as the output for this example. Now let's work through another example, this time with the input string LeetCode. We start by initializing the same set of vowels and converting the string into a list, resulting in LEETCODE. The left pointer starts at index 0, and right starts at index 7. In the first iteration, the character at left is L, which is not a vowel, so we increment left to 1. The character at right is E, which is a vowel. Since we now have a vowel at right and a vowel at left, we swap them. However, since they are the same character here, the list remains unchanged. After moving the pointers inward, left becomes 2, and right becomes 6. In the second iteration, the left pointer now points to E, which is a vowel, and the right pointer points to O, which is also a vowel. This time, we swap them, resulting in the updated list, LEOTCEDE. After the swap, we move left inward to 3 and right inward to 4. In the third iteration, the characters at both left and right are T and C, respectively, neither of which are vowels. Thus, we simply move the pointers again, left increments to 4, and right decrements to 3. At this point, left exceeds right, so we stop the loop. Converting the updated list back into a string gives us LeetCode, which is returned as the final output for this example. For the third example, we handle a short input, AA. As usual, we initialize the vowel set and convert the string to a list, resulting in The left pointer starts at index 0, and right starts at index 1. In the first iteration, both pointers identify vowels, at left and at right. We swap these vowels, updating the list to After the swap, we move the pointers inward. Left increments to 1, and right decrements to 0. Now, since left is greater than right, we stop. Finally, we convert the list back to a string, resulting in AA, which is returned as the output. To analyze the time complexity of this solution, we start with the initialization of the vowels set. This operation takes constant time, O1, because the set contains a fixed number of elements, 10 vowels in both uppercase and lowercase. Next, we convert the input string into a list so that it can be modified in place. This conversion involves copying each character of the string into a new list, which takes O(n) time, where n is the length of the string. Finally, we use a two-pointer approach to traverse the string from opposite ends. Each pointer moves inward, and in the worst case, both pointers visit every character once. For each character, we perform at most two membership checks to determine if it is a vowel, and since set lookups are O1, the total cost for the traversal is O(n). When the two pointers identify vowels that need to be swapped, performing the swap itself is an O1 operation. Even in the worst case where all characters are vowels, there would be at most n/2 swaps, resulting in a total cost of O(n) for swapping operations. After traversal and swapping, we join the modified list back into a string. This operation iterates over all n characters in the list and concatenates them into a new string, which also takes O(n) time. Combining all these steps, the dominant factor in the overall time complexity is the O(n) traversal, making the total time complexity of the solution O(n). Now, let's look at the space complexity. The vowel set uses constant space, O1, because it contains only 10 predefined elements. However, converting the input string into a list requires additional space proportional to the length of the string, O(n), as every character is stored in the new list. The final output string, created during the join operation, also requires O(n) space. Apart from these, the algorithm uses a few variables, such as the two pointers and temporary variables for swapping, which take O1 space. Therefore, the overall space complexity is dominated by the list representation of the string, resulting in O(n) space usage. Let's compare this with a brute force approach to understand why the two-pointer solution is more optimal. In a naive solution, we could extract all vowels into a separate list, reverse this list, and then iterate through the string again to replace vowels with their reversed counterparts. This involves three main steps: extracting vowels, which takes O(n) time, reversing the list of vowels, which takes O(v) time where v is the number of vowels, and updating the string, which takes another O(n). While the time complexity of this approach is still O(n), the space complexity is less efficient because it requires additional space to store the list of vowels, O(v). In contrast, the two-pointer solution avoids the need for this extra list and performs the reversal in place, making it more space efficient while maintaining the same O(n) time complexity. To further break this down, let's analyze the best, average, and worst cases for the two-pointer solution. In the best case, the input string contains no vowels. Here, the two pointers simply traverse the string without performing any swaps, resulting in a time complexity of O(n) for traversal alone. In the average case, the string contains a mix of vowels and consonants. The two pointers traverse the string and perform a small number of swaps, but the overall time complexity remains O(n). In the worst case, the string consists entirely of vowels. Now, the two pointers traverse the string and perform a swap for every pair of vowels, but even in this scenario, the time complexity remains O(n) due to the combined cost of traversal and swaps. Finally, we can mathematically confirm the big O bounds of this solution. The dominant term arises from the traversal of the string, which involves O(n) checks and, at most, O(n/2) swaps. Other operations, such as creating the vowel set, converting the string to a list, and joining the list back into a string, are all linear with respect to the input size n. Since there are no higher-order terms or nested loops, the overall time complexity is O(n). Similarly, the space complexity is determined by the O(n) space needed for the list representation of the string, as all other components require only constant space. This confirms that both the time and space complexities of the solution are O(n). Let's go over some common mistakes to watch out for when solving this problem. First, not handling uppercase and lowercase vowels properly is a frequent issue. Many solutions only account for lowercase vowels like at e, I, o, and u, but fail to include their uppercase counterparts, which can cause incorrect results, especially in mixed-case strings. Next, it's important to remember that non-alphabetic characters, such as digits or punctuation, must remain in their original positions. Some solutions mistakenly reverse all characters, violating this constraint. Another error occurs when trying to modify the string in place. Since strings are immutable in languages like Python and Java, direct modifications will either fail or lead to inefficient code. Additionally, the two-pointer approach, while efficient, can be mishandled if the pointers are not increment or decrement correctly when skipping non-vowel characters. This can result in infinite loops or skipped characters. Finally, avoid overcomplicating the solution. Introducing unnecessary data structures, like extra lists or hash maps, can increase space complexity without adding value. Keeping the solution simple and efficient is key. Now, let's talk about what this problem looks like in an interview setting. First, this is a great example of the two-pointer technique, which is a common pattern interviewers want you to recognize. They might ask you to reduce space complexity, such as avoiding additional lists, to show you can write optimized code. Edge cases are another focus area. You'll need to handle scenarios like empty strings, strings with no vowels at all, or strings that contain only vowels. Demonstrating thorough testing for these will impress interviewers. Be prepared to explain the time complexity of your solution as well. For example, the two-pointer approach achieves O(n) time complexity, which is optimal for this problem. Clear communication is also critical. Describe your thought process as you go, such as explaining why you're using two pointers and how it minimizes memory use. Lastly, interviewers may challenge you with follow-up variations. For instance, they might ask you to reverse only lowercase vowels or to reverse consonants instead. Being ready for these twists shows adaptability and a deep understanding of the problem. Finally, let's explore some related problems and alternative approaches. Similar problems include LeetCode 125, valid palindrome, where you need to ignore non-alphanumeric characters and apply reversing logic, and LeetCode 344, reverse string, which simplifies things by reversing the entire string. Of course, there's LeetCode 345, the direct problem we're discussing here, and LeetCode 917, reverse only letters, which is similar but focuses on reversing letters instead of vowels. Now, in terms of alternative approaches, the brute force method involves first collecting all the vowels in a list, reversing that list, and then reinserting the vowels into their original positions. While simple, this approach requires extra space and multiple passes over the string. The two-pointer approach, by contrast, is both time and space efficient O(n) and O(1), respectively. It uses two pointers starting from each end of the string, swapping vowels as they move inward. However, implementing the pointer logic correctly can be tricky. Another option is the recursive approach, where you reverse vowels through recursive calls. While elegant, this method can lead to stack overflow for large strings and is generally less efficient than iterative solutions. Each approach has its trade-offs, so choose the one that best fits the constraints and requirements of the problem. Great job reaching the end of this problem. We've summarized the key points and takeaways, including the importance of string manipulation and handling edge cases effectively. Remember, consistent practice is the key to mastering coding problems. Thanks for watching, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!